In this lecture, we will learn about making inferences about means of two groups, the two-sample z-test. Welcome to the lecture.
Previously, we examined what's called one-sample tests. Now we're changing things a little bit, not much. We're going to be examining two groups. These are called two-sample tests. We're going to examine two populations, and we're going to look at a parameter, say mu, and we want to determine whether there's a difference, a significant difference between the population means, and as always, we look at the sample means, the sample evidence, and we're going to use that to determine whether the difference between the two means is significant or not. Now, it doesn't have to be means. We can also look at proportions, which we'll do also. But these are all called two-sample tests. And the HO, that's our straw man, is that mu1 equals mu2 if we're dealing with means, which essentially means that there's no difference between the means. Anyway, let's look at the null hypothesis. If we're comparing means, the null hypothesis is that mu1 equals mu2. That's the population mean of group 1 is the same as the population mean of group 2. Or in other words, mu1 minus mu2 is 0, no difference. You're really looking at an HO saying there's no difference, 0 difference between the two population means. So for example, we could be comparing men and women on some measure, like we could look at who does better in college in terms of GPA, and we examine the GPA of men and women, and again, there are other groups too that maybe there aren't enough of them, so we're just looking at men and women. Okay, so the HO is always about the population parameters, and the random variable is x bar 1 minus x bar 2, the difference between the sample means. So we're going to look at the sample evidence to see if it supports the HO that there is 0 difference between the two groups.
If we're looking at the difference between two groups, two population means, the statistic of interest would be the difference between the two sample means, x bar 1 minus x bar 2. So the question is, what's the expected value of that statistic, of that random variable, and what's the correct measure of variation? Well, we don't have to derive it here because this isn't a course in mathematical statistics, but it turns out that the expected value of the difference between the two x bars is mu1 minus mu2, the difference between the two population means. And the standard deviation of this random variable, the difference between the two x bars, is found to be the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. And you'll see how that becomes important on the next slide. So if our sample sizes are large enough, and again, you have to know what large enough means for the company you work for or for the instructor of the class you're taking, or this is easy if the sigmas are known, if the two population standard deviations are known, we could do a two-sample z-test for making inferences in this case. So to get the calculated value of this z statistic, we get that just like every other Z statistic. Every time you see a formula that starts Z equals, it's always the random variable minus its mean divided by its standard deviation. That's why it was so important to figure these things out on the previous slide. So the random variable is x bar 1 minus x bar 2. The mean of this random variable is mu1 minus mu2. And the standard deviation of the random variable is sigma 1 squared over n1 plus sigma 2 squared over n2 under a square root sign. Of course, we can simplify this nicely because by the null hypothesis, mu1 is equal to mu2. So mu1 minus mu2 is 0. And that term falls out, and you're left with the formula on the bottom of the slide. Now, what do we do if we don't know sigma? We're going to come to that in just a few seconds. If we don't know sigma, as long as our sample sizes are large enough, we use S1 and S2 as point estimators of sigma 1 and sigma 2. S1 is the sample standard deviation in group 1, S2 the sample standard deviation in group 2. And just like with one sample tests, we're using the sample standard deviation as a point estimator for the population standard deviation, and we can only do that using a Z if our sample sizes are large enough. If we're working with sample data from two groups, and we are constructing a confidence interval estimator, what we're really doing is constructing a confidence interval estimator for the difference between the two population means, mu1 minus mu2. Okay, we're not, normally we'd be looking at a CIE of mu, but in this case we have two groups, presumably with two means, and we're looking to estimate the difference between the means. We use the formula that you see in front of you. Again, the random variable is x bar 1 minus x bar 2. That's the sample evidence, and that's in the middle, what goes in the center of the confidence interval estimator. We have Z from the table, which gives us our level of confidence. And we have the measure of variation, sigma 1 squared over n1 plus sigma 2 squared over n2. What happens if there's really no difference between the two groups? In other words, we have two samples, but these are just two random samples from the same population. We think it's two different populations, men and women. But if they have exactly the same parameter, it really is the same population, human beings. So what happens to the confidence interval in that case? Well, in that case, it should turn out that there's a 0 in there because if the two means are the same, the difference between the means is 0, and we're looking for that value of 0 in the confidence interval to determine that the two groups really are the same and really are one group. And we'll see a problem like that later on.
Gold standard of medical research is comparing a drug by looking at two groups. You assign people randomly to these two groups. One group will take the new drug, and the other group, we call it the control group, they take a placebo. And in a double-blind study, no one knows who's in which group. In this case, we're looking at number of colds. We're going to test the drug to see if it reduces the number of colds that people get. So we're going to have two groups. Again, one group taking the drug, and another group taking the placebo, and we'll see if the means are different. You look at the sample evidence. In group 1, that's the drug group, 81, we had 81, N is 81, and they were getting 4.4 colds a year with a standard deviation of 0.7 colds. The placebo group, that's group 2, there was 64 in that group, and the mean for them was 4.8 colds with a standard deviation of 0.8 colds per year. Now we can see there's a difference of negative 0.4 colds, 4.4 minus 4.8. Now the question is that difference statistically significant? Is it a significant difference? Or it could just be chance. Anytime you compare two groups, the likelihood is that there'll be some difference. I don't care what. It might be, the big question in statistics is this chance or is it a real difference? And if you want to understand how chance difference, take a coin, flip it 50 times, and you'll get a certain number of heads. Something near 20, you may get to say 23. Take the same coin, flip it again 50 times. It's almost a certainty that you're not going to get the same number of heads. It'll be slightly different, and that's just chance. It doesn't mean anything. That's why we always have to test. The government is not going to let you use a new drug unless you've tested it for significance. You want to make sure that it's different than not taking a drug at all, placebo. As you can see, we set it up. HO is mu1 equals mu2, another way of saying no difference. And H1 is that mu1 is not equal to mu2. Okay, and now we have the Z formula. So we take 4.4 minus 4.8 over the square root of 0.7 squared over 81 plus 0.8 squared over 64. And when you do all the arithmetic, you'll end up with minus 0.4 over 0.127, which is negative 3.15. Clearly, that's in the rejection region. Notice anything to the left of negative 1.96, that's going to be significant. That was less than a 0.05% chance of this occurring. So we'd conclude that the two groups are indeed statistically different. The drug group has fewer colds per year. Now, it would be presumptuous for you to say it's a 0.4 difference, because there's always a margin of error. But for the moment, we know there's a statistically significant difference between the means of the two groups. If you want to construct a 95% confidence interval for the difference, remember your difference was there was negative 0.4 colds. But the reason it's negative is because the lower number was the group 1. If you switched it around, then you have a positive. It doesn't make a difference. All right? But we had a negative 0.4. The drug group had 0.4 colds fewer than the placebo group. Okay, so now let's construct the confidence interval. Construct the confidence interval. Again, you have negative 0.40 plus and minus. Now there's that 1.96, as you know, that's used if you a two-sided 95% confidence interval. Okay, and that number in the denominator, that's in the square root, was the standard error for the difference was 0.127. So you just multiply it and you get the margin of error is 0.25 colds. Basically, that's how you would report it. You found a 0.40 difference with a margin of error of 0.25. Or if you write it out, you'd show that the 95% confidence interval is the drug definitely causes fewer colds, but it could be anywhere, you're 95% sure it could be anywhere from 0.65 colds less all the way to negative 0.15. Notice there's no zero in the interval. So you're basically sure with 95% confidence that the drug group will have fewer colds. Again, the way you would report it, you just say a 0.40 difference, fewer colds, but the margin of error is 0.25. In problem 2, we're comparing men and women to see if there's a difference in standardized science test. I guess somebody, chauvinist, thinks that men are better than women. Okay, well, we're going to see if it's true or not. So we took a sample, as you can see, 100 men, and their average, this is sample mean, was 80, with a standard deviation of 10. The women, their average was 76.5 with a standard deviation of 16. Now, it would be presumptuous of you to say, oh, men beat the women, because as you know, there's always sampling error you have to worry about. So we want to know, is there a significant difference between men and women on the science test at alpha equals 0.05? All right, we're going to set up HO, mu1 equals mu2. H1 is that mu1 is not equal to mu2. And again, we're using O5, we cut it in half, O25 in the right tail, O25 in the left tail. As by now we know the critical values of 1.96 and minus 1.96. Now we turn the sample evidence into a z-score. We end up with 80 minus 76.5. That's the 3.5 point difference. So the men beat the women on the science test. The standard error for the difference, that's the square root of S1 squared over N1 plus S2 squared over N2. It's 10 squared over 100, by the way, that's just 1, plus 16 squared over 64, which, by the way, is just 4. So we end up with a square root of 5 in the denominator. 3.5 divided by 2.24 is 1.56, and we're in the acceptance region. We have no evidence to reject. It's not enough, that 3.5 point difference. It could very well be sampling error. So you'd say in simple English, no statistically significant difference between the two groups, men and women, on the test scores in science. There's no significant difference. As you'll see in a moment, we're going to do the confidence interval for the difference just to show you what happens, but you really don't do a confidence interval. Once you said there's no difference, you're basically claiming that the men and women are the same when it comes to science. So there's no reason to do a confidence interval because you've already said no difference, zero difference. So don't contradict yourself by doing the confidence interval. We're going to show you what happens if you do it. If you do decide to do the confidence interval, anyway, you have 3.5 plus or minus 1.96 times 2.24. So the margin of error is 4.4. When the margin of error is more than the observed difference, there's got to be a 0 in there. Okay, so here's our confidence interval. It goes from negative 0.9 all the way to plus 7.9. Obviously, 0 is in that interval. So basically, that reinforces there's no difference. But again, let me repeat. If you have no evidence to reject HO, if you've, in quotes, accepted it and you can't reject, you don't have to do this. You don't do a confidence interval because you know 0's got to be in the interval. In this problem, we're looking at two colleges. Colleges very often say, our students are smarter than your students, right? We have these arguments between Brooklyn College and Baruch College, and if you're at Queens, it'll be Queens versus Hunter. Everyone's fighting over this. So now one college is claiming that there's a difference in the CPA exam scores between College X and College Y. Anyway, here's the sample evidence. Notice we're looking at a population sample of 260 students, right? Took 100 students from College Y and 160 from College X. And it does seem to be a slight difference, 72.5 versus 74.1. Those are the means. And the standard deviations are 8 and 9.1. But as you know, if we test, let's say, the alpha of 01, we are not sure if the difference is sampling error or not. So we're going to do a statistical test. Well, HO is mu1 equals mu2. H1 is mu1 is not equal to mu2. Since we're testing at the O1 level, we cut the O1 in half. Two-tailed test. We have 005 on the right and 005 on the left tail. The critical values are 2.575 on the right, negative 2.575 on the left. Okay, and then we turn the sample evidence into a z-score. We do the difference between the means and the numerator, which is 72.5 minus 74.1, or negative 1.6. And denominator, we have the standard error of the difference. And we have the square root of 8.0 squared over 160 and 9.1 squared over 100. And we finish all the arithmetic, we end up with a z-score of minus 1.44, which is definitely not in the rejection region. Again, it's got to be to the left of negative 2.575. So like negative 2.8 would have been in the rejection region. Negative 1.44 is not in the rejection region. We don't reject HO, and our conclusion in simple English, there's no significant difference between the two colleges on the CPA exam scores. In other words, it could just very well be sampling error. No college can claim or brag that it does better. And as far as the 95% confidence interval for the difference, you don't need to do that. You know 0 is going to be in the interval. So you basically don't do a confidence interval. You said there's no difference, which is another way of saying that you've accepted 0 as a difference. There's no difference as far as you're concerned. The two colleges do just as well as each other on that CPA exam.
In this problem, we're studying the lifetimes of smartphones produced by company X and by company Z. We took a sample of 60 phones from company X a sample of 64 phones from company Z, and we found an average lifetime of 6.5 years in company X's phones, 5.7 years in company Z's phones, with the respective standard deviations of 1.2 years and 0.8 years. We want to test to see if there is really a significant difference between these two phones, these two companies' phones, and we're going to be testing at the alpha of 0.01. And I'm back. Did you miss me? So here we have our two-sample hypothesis test using Z for the difference between two means. The null hypothesis is that the two means are exactly the same. The alternate hypothesis is that they're different. And if you notice that we've been kind of lazily just saying mu1 equals mu2, we could have said mu x is equal to mu z, mu of company x is equal to company z. But basically, it's simpler and less confusing to stick to the notion that we have a group 1 and a group 2, and that's why you see mu1 and mu2 over there. We're working at an alpha of 0.01, and with two-sample tests, we're always doing two-tail tests. We split the alpha into two equal pieces, 0.5% on one side, 0.5% on the other side. So the critical values from the z-table are plus and minus 2.575. The calculated value of z from the sample evidence, 6.5 minus 5.7 divided by the square root 1.2 square over 60 plus 0.8 square over 64. You end up with 8 over 0.1844 or 4.34. That's a pretty big number for a z. And we are definitely in the region of rejection. It's larger than 2.575. So we reject the null hypothesis at p less than 0.01. It's a very, very stringent test. There is a statistically significant difference between the two companies with regard to the lifetime of their smartphones. We're constructing a 99% confidence interval estimator for the difference between the two population means, mu1 minus mu2. We use the appropriate formula for this. The middle of the confidence interval is 0.8 years. That's the value that we got for the difference between the two sample means. The z-value that gives you 99% confidence, or the central 99% of the distribution, is 2.575. We multiply it by 0.1844, which is the standard error of the random variable. And so 0.47 is the margin of error. And the 99% CIE of the difference between the two means, it goes from a low of 0.33 years to an upper level of 1.27 years. Do you want to know how to retain all this information and do well on your exams? Here you have it. Practice, practice, practice. Once you understand the material, find as many problems as you can and just keep on doing them and do them over. Do them over again. You have problems in the lectures. You have problems in the do it nows, the test your knowledge on the lecture page. You have problems in the homeworks, problems in the handouts. You have a exam prep, practice problems on the handout page. Lots and lots of problems. Thank you very much for joining us in this lecture.